Swayam Prabha. Digital India. Educated India.
Hello and welcome to lecture number 45 of the course Theory of Computation. In the previous lectures, we concluded the topic of computability theory, right, where we saw what is computability, what are languages, what is decidability, what is Turing recognizability, what are some languages that can be decided and that cannot be decided, what are some languages that cannot even be recognized, right, and various techniques to understand this, including reductions, right. We saw all of this, and now we are entering the third part of the course. So the first part of the course was automata theory, where we saw NFAs, DFAs, PDAs, etc. Then the second part was computability theory, and now we are entering to the third part of the course, which is complexity theory, right. So in the remaining time that we have in this course, which is roughly something between 3 and 4 weeks that we have, we'll see a brief introduction to the area of complexity theory, right. So what is complexity theory? It's an area of computer science where we try to understand computational problems in terms of how much resource we need to solve them, right. And this gives this leads to definitions called of complexity classes. So complexity classes are classes of computational problems, so where many computational problems are classified together based on how much of certain resource is needed, right. So something needs a significant amount of space or significant amount of time, we classify into certain complexity class, and if it needs more space, another class, and so on, right. And there are several models of computation, right. So we saw many in our course itself, but there are even more models of computation, and many resources are also there are many resources in these models. So even in the models that we saw, two of the resources that stand out are time and space, right. How much memory is required to do a certain computation and how much time is required. There are also other parameters that are studied, such as randomness. There's a circuit model of computation, so where we try to study the circuit parameters, how much they are needed. There are also there is also parallel computation model, so where we will worry about how much parallelism is there. There are models of computation where there are multiple computers interact in a distributed setting, and the amount of interaction required is considered as a resource. So what I'm saying is that in general there are several resources that are considered for computation, and the goal of complexity theory is to understand computational problems in terms of how much of a certain resource is needed, right. And the most common two resources are time and space, right. So even when we run programs on our computer, we see how much time it takes. Sometimes it takes more time, and sometimes it doesn't take that much time, and we also see how much space it takes, right. So time and space are kind of it is not it's something that everybody knows about, and these are the two resources that we will consider in this course: time complexity and space complexity. Complexity in terms of how much time is needed and how much space is needed. What we will do in the remaining time is to give a brief in the time that we have, we will try to cover some of the basic aspects of time complexity as well as space complexity, and hopefully this will also serve as an introduction to learning more on complexity theory. If you get interested, then of course there are further resources that you can look up to beyond this course, okay, right. So this is roughly what we are going to see from now, right. And from now on, we will only be studying decidable languages, right. So we have studied computability theory, and we know what is computable or decidable problems, and we know what are how to identify languages that are not decidable. So now we are not going to be bothered about that. We are only going to be seeing decidable languages, and we will, in these languages, we will try to see how much time or how much of space we need, right? We'll do a more careful analysis of resources needed, right? Because so far our what we have bothered about is mostly, can this model of computation recognize a certain language or decide a certain language, right? Can DFAs recognize this? Can NFAs recognize this? Can Turing machines recognize this? We never bothered how many steps of computation is needed, how many states are needed, or anything like that, right? We would say two machines are equivalent if they recognize the same language. We didn't really bother about how much time it takes or how much space it takes. From now on, we are going to be more careful about these kind of things, right? Because only then can we say this takes this much time and this does not take this much time, right? So that's going to be the tone from now on. We'll only be studying decidable, so we'll not be even bothered to say that this is not decidable or should this be decidable. We need to convince ourselves of that. Nothing like that. We'll just go and study the languages, assuming that they are decidable, and we will look at the time needed, space needed, etc. more carefully, right? So now without losing much more, spending much more time, let's delve into the 7th chapter of the book SIPSR. This chapter is on time complexity. Okay. So what is time complexity? So running time or time complexity, so both these terminologies are used, of a Turing machine, right? So given a Turing machine, it is deciding some language, right? Or yeah, let's say it's deciding some language. It is the time, so this running time is given by a function, right, called Fn, where what is Fn? Fn is a function of n, and what is n? N is the length of the input, right? So the running time is specified in terms of the length of the input. A longer input may take a longer time to decide, a shorter input may take lesser time to decide. That's the rationale for making it or viewing it as a function on the length of the input, right? So running time is the function from n to n, right? From n to n, where f is the maximum time taken by the Turing machine to decide an input of length n. So f is the maximum time taken by the Turing machine to decide on an input of length n. So different inputs of the same length may take different time. Okay, so if that is the case, we take the maximum. If they are all the same, then the maximum is also the same, right? So given an input of certain length, we want to know what is the maximum time it takes, and that is our time complexity, right? Okay, so first we will be mostly looking at deterministic Turing machines. Later we will get to, we'll define the similar things for non-deterministic Turing machines as well, right? Then let me just also introduce to you the O notation. Perhaps you are familiar with this, but just for the sake of completeness, this is called O notation. This is also called Landau's O notation, right? So if you are given f and g, two functions from integers or natural numbers to real numbers, we say that f is O of gn, f is big O of gn, right? If the limit of f by g is at most a constant as n tends to infinity. Okay, so limit of f by g is at most c for some constant g, for some constant c, right? So this is called f is little O of f is big O of g. We say f is little O of g. Okay, so it's the same, but the O is a smaller O. If the limit as n tends to infinity, f by g is 0, so this is 0, right? Okay, so if the limit is at most some constant, we say it is little O of g. If the limit is 0, we say it is little O of g. So for instance, if f is, let's say, 3n squared plus 2n plus 5, then we say that f is O of n squared, because if you divide f by n squared, you get a constant, it is at most 3, right? So as n tends to infinity, or at most 3.5 if you want to be more comfortable. But we can say f is also the same, f is little o of n cubed, because okay, so I'm not sure, it's little o, so maybe I'll make it a smaller o, little o of n cubed, right? So it's a smaller o, right? So big O means f by g is bounded by an upper bounded by a constant, and little o means it's at most it's equal to 0. The limit as limit of f by g as n tends to infinity is 0. Okay, and these two are used to usually upper bound, meaning we want to say f is at most something, then we say f is O of something, or big O of something, or little o of something. There is also another notation called omega. So we say f is omega gn. This is used to lower bound things. This is used when f by g, the limit of f by g is at least some constant c. Okay, so it's here it is at most, here it is at least. Okay, so it is kind of the opposite of O for some constant c, right? So f is omega of gn if f by g is at least some constant. So then we are saying that f is, in some way we are saying that f is at least some factor times g, right? And if f is both big O and omega of a certain function, right? So for example, if you consider let's say f is 3n cubed plus 5n power 4 plus 10, you can see that f is equal to theta of n cubed. You can both upper bound this by n cubed and lower bound this by n cubed, so that I will leave it as an exercise. So when the same function acts as the upper bound as well as the lower bound, we say f is theta of gn. So this happens when f is O of gn as well as omega of gn, right? So f is theta of gn if and only if f is O of gn and f is omega of gn. So both these things are met. So this is an example. Here f is theta n cubed. So this is a rather kind of there is only constant factor difference between f and g in the asymptotic setting. That is what this means. So here if you look at 3n cube plus 5n power 4 plus, sorry, this is wrong. What I meant is so this, in this case f will be, I'm really sorry about this error, it should be n power 4, because here the term 5n power 4 is the dominating one. When n tends to infinity, this term grows much faster than the other terms, n cubed and 10, right? So this dictates how f grows. So that is why f, the way f grows will be very similar to how n power 4 grows, right? Okay, so this is the theta notation, right? So this is there in the book, and this is also fairly standard if you take any book on algorithms or something. So maybe you can make yourself familiar with these notations, with these symbols. So we have big O, little o, and omega. And sometimes for analyzing algorithms in terms of this much time, this much space, etc., these notations turn out to be helpful, because usually we don't care that much about these coefficients, like the constants that are there. What we mostly care about is the rate of growth. So these things, rate of growth as n changes. So these things don't really matter so much, right? The coefficients 5 or 3 or something, right? So the next definition is d time Tn. Okay, d time Tn. I think in the book in CIPSER it's defined as time Tn, right? Is the set of all languages that are decided in time order Tn, in big O of Tn. So d time Tn is a class of, it's a complexity class, right? So this is the first complexity class that we are seeing. It's a set of all languages that can be decided in time Tn by a deterministic Turing machine. By a deterministic Turing machine, this is also important. by a DTM, not an NTM. Okay, and when I say time, we have not yet defined time. Even here the word time came in. So when I say time, what I mean is right. So I'll just maybe highlight here. Time, by time I mean number of computational steps, because we have only been dealing with the Turing machine, so we know there is no measure or clock that is there, right? So it's like the time means the number of steps needed. So we have how many steps are needed to get to the decision. That's what I mean by time here, right? So running time means we are measuring it in terms of number of steps. Now how that number of steps relate to the actual time itself depends on how the Turing machine is run. But Turing machine being an abstract model, we don't have anything like that, right? But when we translate this to an actual computer or actual processor, these things can be translated. You understand that, right? You can look at how many computations are performed in a certain second. So you have machines that run in gigahertz and so on. So based on that, you can actually translate into an actual measure of time. How many microseconds or nanoseconds or whatever, right? So when it says time, it means number of steps in terms of Turing machine, right? So again, I'll highlight that here as well. So DTime TN is the class of languages that can be decided by a deterministic Turing machine in time Tn, time order Tn, right? So time big O of Tn. Sometimes I'll end up saying order Tn when I mean big O, okay? So OTN, in that much time, what are the class of languages that we can decide, right? And it's important, the deterministic Turing machine is important. That's why I slightly deviated from the terminology used in the book. I am saying D time instead of just time. So that the D here, I'm using it to stress that we are dealing only with deterministic Turing machines, right? So Turing machine is deterministic and could be multi-tape. I'm fine with it being multi-tape. So being multi-tape actually allows the machine to be faster, meaning it can do more computations in a multi-tape setting than it can do in a single tape setting. However, so depending on the function Tn, so right now the way we define it is a deterministic Turing machine and it can be multi-tape, right? And this is okay because even though sometimes we look at specific functions here in for Tn, let's say Tn is okay, Tn can be n squared or n cubed. Usually what we mostly care is if Tn is a polynomial or not. So we care maybe about n squared versus 2 power n. We usually care less about n squared versus n cubed. We care about polynomial versus not polynomial, right? So that's why we are going to be assuming that it is deterministic and it could be multi-tape, right? And finally we come to, or not finally, but we now come to the one of the most important definitions in this okay, this is too dark. One of the most important definitions, which is that of P, okay. Even this is too dark, so we'll just switch back to the old color. So the complexity class P is defined to be the union of d time n power k, where k varies from 1 to infinity. So what are the class of problems or languages that can be decided in d time n, d time n squared, d time n cubed, d time n power 4 and so on. So this, and it's an infinite union that we gather together and call it P. So P means, so the reason for calling it P is that we have n squared, n cubed, etc. So these are all polynomial functions, right? So anything of the form n power k is considered to be polynomial, right? That's why this is called P, and P stands for polynomial, something that can be decided in polynomial time by a deterministic Turing machine, okay? So P stands for the class of languages that can be decided by a deterministic Turing machine in polynomial time, right? And this is one of the most important and most fundamental complexity classes that we will see, right? So we are going to be hearing P much more in the rest of the time. We are going to be discussing time complexity, and even outside this course, if you are reading algorithms or some other branch of computing itself, you may encounter the complexity class P. That is because it's a very significant and important complexity class, because it stands for all the efficient and practical algorithms, right? So P stands for all the languages that have efficient and practical algorithms, right? So any algorithm any language, if you want to decide, we say it turns out that if you think we can decide it quickly or efficiently, it turns out that it has an algorithm that classifies it to be in P, right? And the next thing is that it's a robust class in the sense that, so already I said multi-tape. If you have a slightly different model of computation, maybe without multi-tape, even then the definition does not change, right? So small variations in the model of computation, it doesn't really change. The way it is, in the way things are set up, etc., it doesn't really change. So in that sense, P is a fairly robust complexity class. And finally, I want to stress the difference between exponential and polynomial, right? So terms like this, 2 power n, 3 power n, etc., these are exponential, right? So these are exponential. Whereas polynomials are n squared, n cube, n power 10, etc. These are polynomial. Sorry. Right. So the thing is that whenever we have an exponential function such as 2 power n, and whenever we have a polynomial function such as n power 10, the exponential function is going to grow much faster. So maybe for some small values of n, you will see that 2 power n is small and n power 10 is large, right? So, but then once n crosses a threshold, so it will look something like this. So for small values of n, maybe n power 10 may grow something like this, and 2 power, so this may be n power 10, but 2 power n will keep low in the beginning and then suddenly shoot up. Sorry, I almost went backwards. So what I want to say is that, so this may keep low for initial values, but then immediately it will shoot up. So this is 2 power n and this is n power 10, right? So whenever we have any, this is just the plot for 2 power n and n power 10, but whenever we have any polynomially growing function and exponentially growing function, the exponentially growing function may grow slowly at the beginning, but then very soon it shoots up, right? Because you can see here I am just multiplying by another n, or not even multiplying, right? So when n goes from 100 to 101, it just becomes 100 power 10 to 101 power 10. But when here it is doubling, when n goes from 100 to 101, it is like it's multiplying by another factor of 2. So exponential functions grow much faster. So it doesn't matter what the value of n, what the base of the exponent is, and what the power is in the case of, what the exponent is in the case of polynomial, right? So whenever we have something like 2 power n versus n power 10, the 2 power n will grow faster. Whenever we have something like 3 power n with n power 10, 3 power n will grow faster, right? Assuming that the base of the exponent is something greater than 1, right? So and since exponential grows faster, polynomial is something more slowly growing, polynomial time or polynomial functions are considered to be more manageable. So if a program or if an algorithm has a running time that is growing in polynomially on n, right? So if the running time is fn, where fn is, let's say, n power 6 plus 5 n power 2 or something, this is polynomial, and this is usually considered an efficient algorithm because n power 6 is polynomially growing. Whereas if the running time was something like if the running time was something like f of n is equal to 3 power n plus n squared plus 5n cubed or something, the dominating term here is 3 power n. So this is exponential. So in this case, we say it's exponentially growing, right? So whenever there is we have something that is more polynomially growing, that is more preferred, right? In terms of running time of an algorithm. And P indicates the class of all languages that have efficient algorithms. By efficient, I really mean polynomial algorithms, right? The running time of that is polynomial. Okay. So just a small bit of history. There was this paper that came out in the 60s, I think 1963, I think, called Paths, Trees and Flowers. This is a paper by Jack Edmonds, who is a computer scientist or mathematician, right? And the reason I want to I've kind of pasted a couple of pages from his paper, or one page, some aspects from the paper. So this is the title of the paper, Paths, Trees and Flowers. And he was trying to find something called a matching in a graph. Okay, so I will not get into what is a matching, etc., because it's not that complex a definition, but it's not very important to what I'm going to say next, right? So he was trying to find an algorithm for determining the largest matching or the maximum matching in a graph. Okay, so that's right. I have indicated here for the maximum. So he calls it maximum cardinality matching, right? However, so the thing is that most of the complexity theory really the definitions were given and things took shape in the 70s. So in 1963 there was no formal there was no formal theory that stated that polynomial algorithms are better than exponential algorithms, right? So there was no clear, so that the complexity class P itself was not defined in 1963, right? So the thing is that but then many people had this thought that this is supposed to be efficient, etc. So that is the problem that he faced, in the sense that he had an algorithm for a certain problem which is considered to be significant and important, and he presented that in the paper. Now he wants to sell his result. So he wants to say this runs very quickly, this is very efficient, right? So now it is easy. Now these days you can say this is an efficient algorithm, this is a polynomial time algorithm. But then there was no notion that polynomial time is better. So he had to kind of set the stage for that, right? So he had to kind of motivate why polynomial time is better, why, at a time where this theory was not formally kind of put forth by anybody. But at the same time, he also did not want to kind of spend too much time. So he just added a small section in his paper and he called it digression, right? So he says, I have to explain what I mean by efficient algorithm, right? So, and he says it's just an algorithm and not a formalized, it's not a program, right? It's not a program, he says, right? The computational details are not vital. For computation details are vital. My purpose is only to show as attractively as I can that there is an efficient algorithm, and he goes to the dictionary definition of what is efficient. It is efficient means adequate in operational performance. This is roughly the meaning I want, right? In the sense that it is conceivable for a maximum matching to have no efficient algorithm, right? And what he wants to say is that he wants to put forth a result that there is a good algorithm for finding the maximum matching, right? And he says there is an obvious finite algorithm. Okay, so what does he mean by this? So what he means is that by obvious finite meaning something that runs in bounded time, right? So the time bounded algorithm that he calls it obvious is the brute force algorithm, right? So maybe there is only so many things that you can try, and then you try out all possible options, and then you you find what is the maximum matching, right? But that is usually the brute force approach. Usually is the running time is quite bad, and it is usually exponential, right? That's exactly what he observes also, right? But that algorithm increases in difficulty exponentially with the size of the graph, right? So he wants to do something better than the brute force or something better than exponential, and he wants to know if there is an algorithm that whose difficulty only increases algebraically within the size of the graph. So by algebraically he means polynomially, it's just another term, right? And he wants to contrast between the exponential and polynomial thing. That is what he is doing here. He says brute force is usually exponential, and what I am presenting is much more efficient than that, which is polynomial, right? And then he says the following, which is very interesting and very kind of prescient, if you want to call it that. Right? The mathematical significance of this paper largely rests on the assumption that the two preceding sentences have mathematical meaning. Right? So he wants to say that obviously algebraic or polynomial is better than exponential, right? And assuming that, he wants to go to his algorithm. But then unfortunately the theory was not there then. So he just by putting forth the small section called digression, he just goes on to explain. So let me just read out the rest. I am not prepared to set up the machinery necessary to give them formal meaning, nor is the present context appropriate for doing this. But I should like to explain the idea a little further informally. It may be that since one is customarily concerned with the existence, convergence, finiteness and so forth, one is not inclined to take seriously the question of the existence of better than finite algorithms, right? And then I think the section digression does not end here, it goes on further. What he's saying is usually people just look for finite algorithms or brute force algorithms because they care about existence, etc. But this is one of the papers where he actually says this is better than the brute force algorithm. So that is why he had to kind of motivate this part. Unfortunately for him, the theory was not there then, and the theory would come only like around 10 years later, right? So this was a paper in 60s which actually kind of shows that people had this thought in 60s but did not have or because his result was not about setting up the theory, it was about doing the solving the problem of finding a matching or the maximum matching, right? So he didn't want to spend effort putting forth the theory, but it was clear that he had an idea of what he was doing, right? So this is interesting because it's a paper that preceded all this, but actually touched upon this notion of what is polynomial, what is exponential, etc. So in that sense, it's perhaps considered to be one of the first papers which actually even attempts this sort of a discussion, right? So yeah, you can search for this paper, and if you are somebody who is in the field of algorithms, etc., this is something that you may be reading or you may be interested in reading anyway, even outside the scope of complexity theory, right? It's a paper in graph algorithms.